So this is just a simple open-topped box inequality problem. And so an open-top box is made from a rectangular piece of cardboard measuring 50 centimeters by 30 centimeters by cutting congruent squares from each corner and folding up the sides. Write a polynomial function v at x to represent the volume of such box. So let's start with just drawing a diagram. So if this is our piece of cardboard that we're starting off with, then the longer side is going to be 50 centimeters, and the shorter side is going to be 30 centimeters. Now we're cutting off these little squares from each corner, and we're going to represent the side length of these squares that we're cutting off as x, so they're x centimeters long. And I'm just drawing these lines here to show that these side lengths are all the same. So imagine this is our box now. So we have, if we're folding along these lines here, pretend that was straight. We're folding along these lines here. Then you have this box with the height here. Oh, this is the length. This is the height again, the height, the width, height. And it's starting to look like a box. So this is our box. Now that means our length of this box is going to be the original 50 centimeters minus 2x, because there are two x's here. So this length here in red, so the length of the box is going to be 50 minus 2x. And now we're going to do the same thing for the width. So the width of the box, so this red piece over here, is going to be equal to the original 30 centimeters minus 2x, because there's two x's here. So minus 2x, and then the height of the box is just x, because remember this is a square, so the height of the box is just x. So volume is equal to length times width times height. And v at x is just the volume in terms of x. So we already found that out. So the length in terms of x was 50 minus 2x, and the width was just 30 minus 2x, and the height was just x. And where x is centimeters, and these are all in centimeters, so don't forget that. So now we're just going to expand and simplify. So we're going to continue to expand and simplify. So we get 15 in x minus and plus 4x cubed. Now let's just write this in descending order. So 4x cubed, and group these terms together. So minus 160 squared plus 1500x. So now you have to remember that this is a real world problem. So yeah, we have our polynomial function that represents the volume of this box, but the problem is we can't have negative side lengths, and we can't have side lengths that are equal to 0, because try folding a box with a length of 0. You can't do it, and you can't have a height of 0, otherwise it's just a piece of cardboard. And so that's our problem here. So we need to have our length greater than 0 and not greater than or equal to 0, because it can't equal 0 either. And we need to have our width greater than 0 and our height also greater than 0. Now we need all three of these things in terms of x, so we can put a restriction on the domain for x. So our length in terms of x was 50 minus 2x. Therefore, 50 minus 2x must also be greater than 0 from this above criteria. And we're going to do the same for the width. So let me just put a squiggly line. So the width in terms of x is 30 minus 2x. So that also must be greater than 0. And the height is just x. So x must be greater than 0. Now we want all three of these things with x on one side of the inequality and some number on the other side. So we're just going to rearrange these. So now we have 50 is greater than 2x. We're going to divide by 2 on both sides to isolate for x, and we get this. 25 is greater than x, but it looks nicer when we write it this way. So I'm just going to do that. X is less than 25, and that's 25 centimeters. And now we're going to do width. So 30 is greater than 2x, and divide by 2 on both sides. And now we get 15 is greater than x, but we're going to rewrite that. X is less than 15. And here we already have x is greater than 0. So these are our three criteria. Now this is important because all three of these criteria need to exist at the same time or need to be met at the same time. Because if one of them isn't met, then the one that isn't met is going to cause that side length to either equal 0 or to be less than 0. And that can't happen in order to have this box. So in order to have this box, we need our height to be greater than 0, and we need our width to be greater than 0, and also our length to be greater than 0. And in order for all three of these to be greater than 0 at the same time, all three of these x criteria need to be met at the same time. So when we're finding where these criteria are met at the same time, what we need to do is find where they intersect. So for that, I'm going to draw a number line. So this is my number line. I'm just going to put 0 in the middle, then 15, then 25. These are all centimeters, of course. And I'm going to use different colors for the length, the width, and the height. So I'm going to do the length in black. So the length needs to be, so for length, x needs to be less than 25. So not including, and that's why I'm going to use this hollow circle. So it's not including 25 and it's less than, that's why the arrow is pointing in this direction. And it goes on indefinitely, so that's why there's an arrow there. So now for width, I'm going to use red. So red for width, black for length. So for width, x needs to be less than 15. So I'm going to put a hollow circle here, show that's not including 15, and it goes on indefinitely in that direction. I'm going to use green for height, so x needs to be greater than 0. So I'm going to put a hollow circle there to show it's not including 0, and it goes on indefinitely in the positive direction. So we need to find where these lines intersect because we need them to all exist at the same time. So I'm going to use a highlighter now and highlight where they intersect. So the lines all exist. So these x criterias are all met within this highlighted area, excluding the hollow circles. So the x criteria is met where x is between 15 and 0. So when x is between 0 and 15 centimeters, the length, the width, and the height are all greater than 0. So that is important because this is a real world problem. So our domain for this via x polynomial is going to be x is a member of real numbers such that x is between 0 and 15, where x is the length of the congruent squares that are being cut off in centimeters. So now we're on part B of this problem. Determine the range of side lengths that are possible for each square that is cut out and removed that result in a volume greater than 4,000 centimeters cubed. So here we just have via x, so the volume in terms of x, of the box that we discovered earlier in part A. So that is 4x cubed minus 160x squared plus 1500x. And we know that the domain for this is that x needs to be between 0 and 15 at all times in order for this to work in the real world. So now we need to find the range of side lengths that are possible for each square but that result in a volume greater than 4,000 centimeters cubed. So we can write this as an inequality. So the volume is 4x cubed minus 160x squared plus 1500x, and this needs to be greater than 4,000, so 4,000 centimeters cubed, because the resulting volume would be in centimeters cubed. So it needs to be greater than 4,000. So what we're going to do is move the 4,000 over to the other side. We're going to end up with 4x cubed minus 160x squared plus 1500x minus 4,000 is greater than 0. And now what we need to do is find the zeros. So we need to find the values of x that result in 0. So because this is cubic, it's a bit harder to do this. But what we can do is see that 4 is a common factor of each of these terms here. So of here, 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 and here. So to make this a bit easier to factor, I'm just going to factor out the 4 from the get-go. So 4 cubed minus 40x squared plus 375x minus 1000 is greater than 0. And now because there aren't any more common factors, we have to figure out how to factor this. We can either do by trial and error, or we can use the rational roots theorem. So we're going to use the rational roots theorem to help us find some potential factors for this polynomial, for this cubic function. So what we're going to do is we're going to take the coefficient of the leading term, so of the cube, of the x cubed, and we're going to take the coefficient of the x to the 0, so just a constant, so that's negative 1,000. And what we're going to do is we're going to find the factors of each of these coefficients. So the factors of 1 is just 1, and the factors of negative 1,000 are, there are so many. There's 1, there's 2, 4, 5, 8, just to name a few. So there's a whole bunch. And so to use this theorem, the coefficients of the leading term, let's just call that, I don't know, let's just call that A, and the coefficients of the last term, so the constant, let's just call those B. So B divided by A, and we're going to find both the positive and negative values for this. Those values here, we'll call them C. So those values, when plugged in here into this equation that I'm highlighting here, so when you plug in those C values into here, if you get 0, then that means that that is a 0 and that is one of your factors. So I already did this and I found out that 5, if I plug in 5 into this equation, we end up getting 0. So what that means is, x is equal to 5. And so if we were to rearrange this, we get x minus 5 equals 0. So x minus 5 equals 0, and x minus 5 is one of our factors. So that means when we plug in 5 in here, this whole bracket will go to 0, and whatever is being multiplied by this bracket will also go to 0. So that's important, and that means we know that we can rewrite this polynomial as 4x minus 5 times some other polynomial, and that's all going to be greater than 0. So to figure this out, we need to divide this section by x minus 5 to find out the remaining portion of the polynomial. So we're going to do that over here. So what we're going to do is x minus 5 goes into x cubed minus 40x squared plus 375x minus 1000. And you shouldn't get any remainder, and you're going to find the answer to be x squared minus 35x plus 200.
So now that we have the remaining part of the polynomial, we can rewrite the entire equation for volume in terms of x in its newly factored form. So we have 4 and x minus 5 as a factor, and then the remaining portion, that's x squared minus 35x plus 200, and this is all greater than 0. And now we want to factor again, so this quadratic, and you'll notice that it's not easily factorable, so we need to use the quadratic equation, and that is x equals negative b plus minus the square root of b squared minus 4ac, all divided by 2a. And so a in this case is the coefficient of the leading term, so the x squared, which is just 1. So a equals 1, b is the coefficient in front of the x, so that's just going to be negative 35, and c is going to be 200. So plugging this all in, we get negative 35 plus minus the square root of b squared, so negative 35 squared, minus 4 times 1 times 200, all divided by 2a, so 2 times 1. And that gives us 35 plus minus the square root of 1,225 minus 800, all divided by 2. And that simplifies to this. 425 over 2. And the square root of 425 can be rewritten as square root of 25 times the square root of 17. And we know that the square root of 25 is 5. So that's how we get 5 root 17 over 2. And so that's our exact answer. And when we add, we get x1 is approximately equal to about 27.81, and x2 is approximately equal to 7.19. This is when we're rounding to the nearest hundredth. So now we have the exact values and the approximate values for x that give us 0 when we plug it in. So what we're going to do now is rewrite this in its newly factored form, and I'm going to use the approximate values, but right next to them I put the exact values, so you could use either one. So now we're going to have 4 times x minus 5, and we're going to rewrite this part in factored form with our newfound factors. So we're going to have x minus 27.81, and we're going to have x minus 7.19, and this is all greater than 0. So I created this chart here. So I created this chart based off of this number line at the bottom. So you can see on this number line I put 5, 7.19, and 27.81. And I put these here because there are zeros. So they're the numbers that when we plug it into this equation over here that I highlighted will produce 0. So this is important because when we have a graph, so let's just draw any random graph, at these zeros, so below that zero, so sorry, to the left of that zero, the graph is negative. To the right of it, so between these two zeros here, between these two zeros, the graph is positive. Between the other two zeros, the graph is negative, and after that zero, it's positive. Now this is just one graph, one random graph. We don't know what our graph looks like, but we want to find the area of the graph where it is positive. So that's why I put these zeros down, and I also put in our graph here, I put x is less than 5. So we're going to figure out if the graph is positive or negative when x is less than 5. We're going to figure out if the graph is positive or negative between 5 and 7.19. So between those two zeros, between these two zeros, and after this zero. And so I just put the factors of the graph here on the left side, and all we're going to do is plug in a number that fits that criteria. We're going to plug in an x value that fits that criteria and see what the resulting sign will be. So let's just go through this. So for this first row here, it doesn't matter what we plug in x because there is no x. And this is positive 4, so this will always be positive. It doesn't matter. It'll always be positive. Now, let's look at this bracket right here, x minus 5. So if we plug in something that's less than 5, so let's just think of any example. So like 4, for example, 4 is less than 5. If we plug in 4, 4 minus 5 is negative 1. So the resulting sign will be negative. And so let's do the same thing continuing down. So let's use like 0, for example. 0 is an easy number to use. So we should have used 0 from the beginning. But if we use 0, 0 is less than 5, right? So 0 minus 27.81 is going to be negative. So we have a negative sign here. And 0 is less than 5, so 0 minus 7.19 will also be negative. So now our resulting sign is positive times negative gives us a negative value, times negative gives us a positive value, and times another negative will give us a negative value. So our resulting sign is going to be negative. And now I'll let you complete this chart on your own, but the resulting signs are going to be negative, positive, negative, positive. So what are we interested in? So let's go back over here. So we're interested in the resulting sign, so for when all of these are greater than 0. So let's go back to the graph. And greater than 0 means positive. So we want our resulting sign to be positive. So v at x is positive when x is between 5 and 7.19, and when x is greater than 27.81. So that's important here. These two things are not occurring at the same time because x can either be between 5 and 7.19 to produce this positive value, or it can be greater than 27.81. So these things are not occurring at the same time because you can only plug in one x value at a time to produce a volume that is greater than 4,000 centimeters cubed. You would think we have our answer, but you have to remember that this is a real world problem. So we have to go back to our original idea that our side lengths cannot be negative and they cannot be equal to 0. So these things are occurring at the same time. So what I mean by that is that if we choose to go with an x that's between 5 and 7.19, we have to make sure that at the same time we don't get a negative side length, and at the same time we don't get a side length that's equal to 0. So that's our first case. And our second case is if we decide to go with an x that is greater than 27.81, we will get a volume that is greater than 4,000, but we need to make sure that our side lengths are also not negative and also not equal to 0. So we're going to do that on the next page. So now we have two cases. We have case 1, where you choose an x value between 5 and 7.19, and that produces a volume greater than 4,000. And the x value at the same time has to be between 0 and 15, because we can't have negative side lengths or side lengths equal to 0. So these two events need to occur at the same time. And we have case 2, where x is greater than 27.81 to produce a volume greater than 4,000 centimeters cubed. And at the same time, x needs to be between the 0 and 15, which we found out in part A for the same reason. So we can't have a negative side length or a side length equal to 0. So because these events are occurring at the same time, in case 1 and case 2, we need to find each individual case's intersection. So I'm going to draw a number line with these critical values so we can find their points of intersection. So I'm going to put 0 here, 5 here, 7.19 here, and 15 here. And so I'm going to use green to show this interval. So x is between 5 and 7.19. So using hollow circles, I'm going to draw this here. And then using red, I'm going to show this interval here. So x is between 0 and 15. So as you can see at this highlighter, they intersect here. So excluding 5 and 7.19, and we have this interval here. So x is a member of real numbers between 5 and 7.19. Now for the second case, we're going to draw another number line and put our critical values. So 0, 15, and 27.81. So now that we have these here, I'm going to use green again for the top part. So for the top criteria, x is greater than 27.81. And then for the bottom one, I'm going to use red. So x is between 0 and 15. Okay, so as you can see, these events do not intersect. So they cannot occur at the same time. So these two events do not occur at the same time. Because of that, case 2 is inadmissible. We cannot use it. So the only case that we refer to, the only case that we use is this one. So where x is between 5 and 7.19 centimeters, and that is because it meets both of the requirements. It meets the volume requirement because it produces a volume that is greater than 4,000 centimeters cubed, and it meets the side length requirement. So it produces a side length that is greater than 0 because we cannot have negative side lengths and we cannot have side lengths that are equal to 0. So that is why this is our answer.